Are you ready? Nice. So here's what we're doing, Joseph. Will it play in the So errors could be broken up into two classes, right? We could have errors that are what? Random. And we could have errors that are right there, just to give you an idea. You have the notes with a little more meat in it, right? Right? Some more definitions and those. Nice. So you have random errors and systematic errors. Random errors are created by who? By the experimenter, right? So the experimenter creates random errors, right? And random errors, for example, you're taking a reading and you don't take the reading high level, right? You have problems here. AC affecting no. AC is what type of error? What type of error will that be? Random or systematic? That'll be systematic. That'll be environmental, right? But the experimenter can make errors like reaction time and so on, right? So what the experimenter does to reduce these errors, to reduce random errors, what they do is anybody knows what they do? So if you have a pendulum oscillating, what you do to try to just stop it? Repeat it, right? So what they do is they repeat and find the average. They repeat and find the average. What this does is this reduces your random error, right? And if your random error is small, what do we call that experiment? If you have small random errors, what do you call that? Begin with P. Parallel. Now, small random errors means that your experiment is precise. So a precise experiment, small random errors, right? So you could create a small little chart to explain everything about random errors. Are you okay with that? Nice. If I have a little bullseye here, how do you think I could show precision? Shoot the arrow and where it has to go. All right, but that's more than precise. So if you shoot something 20 times, how do you define a precise experiment? Right, if they all end up real close. Right? So a precise experiment could be something like this. Everything real close. Right? Accurate, on the other hand, will be close to the actual value. Okay? Precision means you do this experiment properly. So you get the same results all the time. That's okay? Systematic, on the other hand, has to do with apparatus and what? And the same thing Nathan was talking about. Apparatus and environment. That's okay? Right? How do we avoid or reduce systematic errors? What do you do? Change the apparatus. Change apparatus or what? Or what else we can do? Suppose you go on a scale, but the scale not at 1. Sorry, the scale not at 0, it's at 3. What you have to do? Right? You have to try and 0 it or right, minus 3 from the values. So you can change the apparatus, but in the lab you probably don't have the opportunity to change it. What you have to do is apply a little formula, right? You have to apply a little formula. Right? Or if it turns out to be environmental, you have to cater for the environmental. Suppose it's environmental, what you're seeing is in errors. Like in a heat lab, what you always say, assume that heat loss to the environment, right? So all of the heat didn't go to the substance. Some was lost in the environment. So all that is explaining why I had a systematic error, right? So what do we call a small systematic error? accurate. So what would something accurate look like? Accurate will be right on or real close to the bullseye. That's okay? What would be an accurate and precise experiment? All of them on the bullseye. Close together on the bullseye. Are you okay with that? So you need in your mind to be able to separate what's a random error and what's a systematic error. Are you okay with that? And of course, because of errors, we have to learn to do calculations. So we have to learn to do error calculations. All right? So let's identify what's an error, right? Let's say we have something like this. All right. So watch this here. Oh, you can copy down the chart. The chart is a nice way when I want to review your work, you create a chart. Remember, you can just go to our chart, you take it notes and drop it in there. And we create the charts and physical things there, right? Summarize everything. So you have to learn and read it and make sure you know what those things. But yes, all of these talk via Huh? No, let's share this, let's share it code. So you guys just all the time. Let's share it. Huh? There's one. All right. So you wanna understand errors, right? So what's the smallest possible reading we can get here? 0.1, right? So here will be 0.1. You'll see now online. Here will be 0.2, 0.3, 0.4. Right? So if I give you something to read off, let's say we have to find the length of a piece of wood. And the word reads somewhere here. What's the best you can do? You might say it's 0.25. Yeah, it looks like in the middle, right? Could you do any better than that? Could you say like 0.255? All right. Right? So this here, oh, so that was me. So that was the reading we end up with, right? So what we sure about? We are sure that this reading lies between 0.2 and 0.3. 100% sure. Correct? And we are 100% sure? Right. So our error here could be plus or minus 0.05. Right? It could be, this value could be plus 0.05 or it could be minus 0.05. That's okay? Can we get any smaller than this? No. That's all we can get. So how do we end up with this 0.05? The general rule is what? Half of the smallest reading. That's okay? Half of the smallest reading. You understand why? It's important in physics you understand why and not just this, right? Are you okay with that? So our value here can only lie here, guaranteed. Right? There's no need put in 0.1 because we know in between 0.2 and 0.3. Right? So we might be wrong by 0.05, which is technically half of the smallest. Everybody okay with that? So what does that mean? It means that every quantity Q will have some sort of error, delta Q. Right? This is called the error or the uncertainty. That okay with that? This is the error or your uncertainty. So now let's see how we can put things together to do a error calculation. Copy down. Right? So now, how do we deal with errors, right? So let's look at an example here. I forget. All right, so what is here? Let's say I gave you two quantities. Already?
Yes, sir.
Let's say I gave you two quantities, A, which has a value A and an error lowercase a, right? B, same thing. Error in B. Now I said to find A plus B. How would you find A plus B? A plus B, you'll get a value, right? So to get A plus B, you add the A and the B, of course. And then you add the errors. So you add the error in A, add the error in B. That's okay? Add the errors and add the value. Suppose it was A minus B. You minus it A and B. And what you gonna do with the errors? Nope, never minus errors. Because here's what you're saying. You're saying that you use two apparatus with two sets of errors, where you get less errors. Supposed to get more errors, right? So in short, what that means is that we don't ever, never subtract errors. So you never subtract errors. Okay? Never subtract. If you use an apparatus 10 times, you have 10 sets of errors. Okay? Every piece of apparatus has error. Right, Joseph? Yeah?
See, Joseph, probably
Right, Joseph? Joseph, what I was saying there while I wasn't paying attention is that you always add errors. Right? Never minus. Okay? So although I asked you for A minus B, you still add the errors. Why do you find B? Because now should be right? Because once you do an experiment and it keep using some errors, and they keep adding to one of them. You find the average, then you see is that you use 10 apparatus, so you have one which have 10 sets of values. Because you find the average, that's 1.1. So you end up with 2.1 is the end, but you should say 0.1, that's 10. Right? You can't see one, you can never reduce the error the next term. Right? Every time you use something with errors, you have to add that total, add that total. Because your value getting less and less after. But you're okay with that? Nice. Suppose we had something like this. Suppose we had multiply. Let's say we had a multiplied by a squared. Yeah, I can see why those keep picking on you. You're in trouble here. Right, so what's here you done? Right, you done what's here? How would we find a squared? A squared will be a multiplied by a. But what you'll do with the errors, multiply them. Now, add up the errors. There's two a's, right? So you're adding up a and a. Right? Are you okay with that? Suppose it was the square root of b. What you would do? Square root b, but what you'll do with the errors? What you will do is you'll put the error of a to the power of a, sorry. You'll put the error of b to the power of a half. Okay? Because technically you're using half of it. So it'll be half error. Right? You can look at it that way. Right? When I give you some numbers, you will see how it makes sense, right? So generally, if I ask you to find something like this, a squared b cubed divided by, okay, I don't want no letters. I can add in one more letter for you here. Right? Let's say I give you something like this. How are you going to find the error here? Right? What you say, right? Joseph? To find the error here, what you will do is something like this. You will find, you'll work it out like normal. Take the value for a squared, take the value for b cubed, take the value for c, put it to the power of 4. That's okay? And then you have to cater for all the errors in here. Okay? I'll show you how to get it. Are you ready? What is here? Suppose I give you something like this, and I want you to find the error in this formula. Right? We'll put some numbers, say that's not right. Suppose I want you to find error here, right? A squared, b cubed, and c4, right? How are we going to find error here? So how do we get p? To get p, we use these values here, a, b, c. So that would be a squared, b cubed over c, right? How do we get error now? You take this value, a squared, b cubed, c cubed, and you multiply it by the fractional error of each one, right? So it will be the error in a all over a plus the error in b all over b plus the error in c over c, right? But it's two of these. It's two of these, right? So you multiply it by 2. There's 3 of these. So you multiply it by 3. Already divided, there's 4 of these. So you multiply it by 4. All right? Before I think it hard, let's do an easy example. Copy it up. Copy it down. Before I think it hard, let's do our example and come the calculator, right? Copy it down and let's do this all together. Copy it down and let's do this all together, right? Ready? I want to do this one together, otherwise I don't get. Let's do this one together, right? So we need to find kinetic energy and the uncertainty. And I gave you the uncertainties here. How do we find kinetic energy again? A half mv squared. So the first part that we need, the first part is to find kinetic energy before we get the error. A half by 5 by 2.5 squared. Right? You have to using these values here. How much is that? 15.63, right? Let's leave it like that. Right? Now we're going to get the error to the material. Okay, so help me out here since you have the picture on your phone. Right. Help me get the error now. Use this thing. How you get the error? So to get the error in the kinetic energy, real simple. Find the kinetic energy, which we found already, and multiply it by the fractional error to the powers here. Right? So you have mass, right? So it will be the fractional error of mass plus the fractional error of V squared. Well, by 2. Okay? One of this, two of this. You okay with that? Sure? Kinetic energy, work it out already. 15.63. Error M is what? 0.2. M is 5. Error in V is 0.01. And value is 2.5. Right? When you work this out, that will be a error. Okay? So it's simply the value you got by the fractional errors. Yeah? Tell me how much you get. Of course, it should be much smaller than this, right? How much? 0.75. How many just get up? Want to reach yet? Come on, you get. Oh, wait, he messed up. I didn't write it. Well, I didn't mess up. Take your time. Everybody follow how I got this formula here. Joseph, follow how I get it. So if I had cube here and cube, how should I change? Giving on it. What would it be? If it was m cube, what would go in front here? 3. Because what? V squared, 2 in front here. Right? So based on the power goes in front. 0.75, okay. 0.75. So the final answer is 15.63 plus and minus 0.75. Yeah? Any questions? Make sure it's in the SI units, yeah? You have got constant. Yeah, was enough. Right? Please remember that the half is a constant, has no errors. Errors only occur for quantities that we have to take measurements for. Right? Copy it down. Any questions online? Did I share any bloopers yet? This whole one here? Try this, please. Try that here. Have a little trick to you though. What they ask for? Find what? G. But you have to make G the subject of the formula, right? Go ahead, have fun. Make G the subject of the formula. Okay, okay. Make G the subject first, right? You all got it hand, will you? Who not you? Son. Very good at that. But go one time and tell it in the office. No. Yeah. Yeah, the be no come on. Just tell them to add yes to the one. Yeah. See that one for them. I'll check. You can try and think, you gotta make easy stuff because I don't want to skill. Not square both sides. Square both sides first. Right? So I don't want to see what you end up with, right? I recognize that you'll get a little cross more again problem. So when you square both sides, you'll get t squared is 4 pi squared L on G. Right? And then you want to make G the subject, right? So move across t squared on 4 pi squared L on G. Then cross multiply. GT squared L 4 pi squared. Last part, move across t squared. Right? So it's L, you can leave it like this, 4 pi squared all over G. Sorry, t squared. Right? Square both sides and then make G the subject of the formula. That's okay? Now have fun doing that. Right? You have L and you have T. You don't need anything else. Right? Find the error there. I'll go on the board and do it first now. Square root. When you square root. Get out my already. Awesome. Take time, right? It's equal. Good school, right? Great school. Done? Yes. Any problems? Yeah. Well, when you're working out G, no, you leave all the 4 pi squared. Right? For in the uncertainty, you're only working with L and T squared. Right? But when you're working out G, initially you're leaving in the constants. Remember, the constant has no error. Right? You see how I left out half here? That you're leaving out 4 pi squared when you're calculating this. Right? I'm gonna do this now. Right? Your value should be close to something and you know, right? Close to 9 point something. What you got? How much you get? 9.7. So we're heading at that. Oh. Yeah, 9.7. No, wrong, no. Right? So we have G is equal, I'll go on it. Online, I'll show you that's now, right? Check out your workings. L is 1.150. Check your SI units when you're doing questions like this, right? Or your next parents double up, right? I don't know. Whoa! Yeah, what's the all this? So like it will be an hour for Q and an hour for physics. Half five. Yeah. Yeah, that's breaking. Just know what you can do it in the week after. Week after I won't be getting 11. Right? So next week, which is the fourth. Number one. Huh? No, I was going somewhere with my little son. Half five. Next week. So you get a little break, you get like a 20 minutes. So that's what I only have to do. So 40 next week. Only next week. Oh. Only next week. Right? Only next week, right? Right. Let's see what happened here, right? I will send a message on the group to remind them. Right, ready? Watch here. So first thing first, we have to find G. So that's 4 pi squared. This is the only time we use the 4 and the pi constants, right? L is 1.15. Make sure it's the right unit, correct? All over 2.16 squared. How much is that? 9.73. Right, 9.73. One more decimal, please, just in case. No, whatever, that's 9.73. All right. Next part, you want to find the error in G now, or the uncertainty in G. That will be G by, so the one G by error in L on L plus the error in T on T, but T is what? Squared. As I was saying, 4 pi squared does not contribute to the error because of constant. Now you work this out, 9.73 by 0.05 all over 1.15 plus 2 by 0.01 all over 2.16. When you work it out, how much you got? 0.13. So your final answer for G, always write the final answer. It will be 2.73 plus and minus 0.13 meters per second squared. That's the error calculation. That's all it. In between, you just have to understand what is fractional error. That's okay? Suppose you do a lab and they do give you this. What you have to look for? Half of the smallest reading. Okay? So if you get a value, but if they didn't tell you what the error is, you have to go to your apparatus, look for the smallest reading and divide it by 2, and you'll get it. Okay? Pay attention to these units, right? Let's go again. Next one. Right, we have one line here still. Judah, again, Emma. You're okay, Tariq? Right, nice. right? I'll leave an audio underneath, right? I'll leave an audio underneath. Find the error here. Find the error. If we do one more after this, we gotta work fast. We have one more. Right in the hand. I have the audio. Adrian. I'm just shocking. Add up. Are you done? Yeah, so you're finding specific gates and teeth, right? I can't really zoom out to that part that I went to see. Look at it. It's a give right here. Better read it. Sure, I didn't read that. Better read it. They gave you the formula, right? And they want you to find L. Find L and the uncertainty. There's a past paper. There's find the uncertainty and it. Yeah, go. Plus and between, right?
I get it, I get it.
All right, let's go. You're done? Right. One common mistake here is that people forget to write the mass of 9.9 by 10 to the minus. Write it out. Well, it was that. You're laughing at? What they chop down. Right, so we have power. We have power is 54 plus and minus 2 watts. Mass 9.9 plus and minus 0.1 by 10 to the minus 3. And time is equal to 300 plus and minus 2 seconds. And the formula they gave us is P T by ml. Right, let's go. L is what? L is PT over M. So I can work it out one time, right? 54 by 300 all over 9.9 by 10 to the minus 3. How much is that? Right, what you can do is give me by 10 to the power of 6, I think. Yeah, how much? 1.64 by 10 to the 6. 10 to the 6, right? Yeah. And now error in L is what? L multiplied by the error in P on P, error in T on T, error in M on M, and put the value in front. Any value? No, 1 on 1. Okay? So that'll be 1.64 by 10 to the 6 by error in P is 2154. 2 over 300. And the error in M is 9.9. 0.1 over 9.9. Question. Hey, that question here. Do I have to write 10 to the minus 3 here and 10 to the minus 3 here?
Yes.
No, because they would what? Cancel off, right? So when you work this out, your answer is what? Put it by 10 to the 6, huh? So it's easy for you now to write your final answer. All didn't get it? All didn't get it?
Something.
1 point. Put it at 10 to the 6, huh? Nathan, you get through? Yeah, how much you get? By 10 to the 6?
I get 8.8. I get 8.
10 to the 6? This bar should be smaller than this.
8.8 by itself to be.
That's
Yeah,
right.
it's actually. Yeah, 10.4. Then 8.8. That's 1.0 by 10.6.
Right, so it is 1, 2, 3, 4, 5, so it's 0.08
Yes.
by 10 to the 6, right?
It's like you.
Yeah, 0.08.
0.08. 0.088. Right? So your final answer can be written like this: 1.64 plus and minus 0.088 whole by 10 to the 6. Right? So you put them all to the same power value here, right? That's okay? That's the reason why I put the same thing. Yeah, how you put them together. All right, you can squeeze in one more, buddy. Huh? Allow me to play that. Like this, since I get one big block right there. Huh? Everybody okay with that? Everybody okay with this? Online? Just follow the process. So regardless of how the formula looks, same process, right? Just make sure it's the right units when you're working it out. All right, guys. Online, that's it there for